Hey everybody, Dave Limburg in Hong Kong with a new episode of THD Podcast. Thanks for checking us out. Be sure to subscribe, like, and share and all that good YouTube stuff, or I guess Spotify or wherever you're watching or listening to this. Today we have a company from France building loudspeakers in France, Kartesian Audio. And what I understood is that they're focused on materials and some custom designed parts like spiders and different specialty design components, and they make the parts, and it's all focused around making proper high quality transducers and specifically around higher capacity transducers. So what does that mean? Does that mean better input to output ratios? At any rate, we're going to find out today. But without delay, let's give a thank out to the Alti Association. Cartesian's a member, and so we're happy to have Barry Vogel help arrange this presentation interview today. So be sure to get involved with Alti, and they're a great organization. So without delay, we've got Simon Weston in Japan. Good afternoon, Simon.
Good afternoon.
And we've got Clement Lambert coming into us from France. How are you doing today, Clement?
I'm fine, thank you. Hello,
Okay,
everyone.
so I always try to summarize what I've read about your technology in one sentence. But perhaps you want to get into a presentation and explain to people exactly what Cartesian's all about.
So a few words about Cartesian. So as I said, we are a company located in France, and we are focused on the quality and innovation. This is very important because there are many driver manufacturers around the world, and everyone has his own specificity. And for Cartesian, what we want to do is better driver, very high quality innovation. We are not focused on a very large quantity with a very low price. We prefer to find a way to make the audio world progress. In the company, we integrate the engineering and the production. For the engineering, we try to work with the best tools available, Clipper for the measurement, Loadsoft, MATLAB, and so on. And for the production, we design the production line to be able to have some quality control at every single step of the assembly. I mean, we do not wait the end of the production to check if the products succeed the test with a basic frequency response. We control every single part from the beginning before the assembling. We measure the magnetic field in the motor structure immediately after we charge the motor structure, and so on. And at the end of the production, we have a system which automatically print a QR code on the driver. And this QR code is linked with the parts we use for this production batch. So we can follow and track every parts we assemble. And if we found something wrong with the spider or the voice call, and we can immediately put it out of our stock. Our main activity is to design specific drivers. So I will take an example just after. And we also have a distributed projects lineup. We have 2 distributors. We do not want to have many distributors everywhere, because next we start a war about prices, and I don't want to do it. I just want to work with a distributor who love their jobs, serious, and that's it. So for the European Union, we work with TLHP. They are located in France. And for the US market, we work with Suround. So if you want to order some regular Cartesian drivers, you can to go there. Okay. This lineup has been designed to be a platform for specific products. So I can take some example about that. So the first example I take is a specific exclusive driver we designed for a high-end brand. And for this driver, as we did for many others, we design every single part of the driver. The aluminum frame has been designed by the designer of the customer. It's an handmade drawings. Next, we do a 3D. We do the aluminum injection tooling. We design every single part to reach the performances that the customer wants to reach. So this is on the screen. I can show you the real one. It looks like that. So you can see the huge motor structure, the large voice cord, the aluminum frame with the very specific design. So this is an example of what kind of specific driver we can produce. Next, about the distributed lineup, I take another example, which is a small subwoofer, which is so small that it can extend in the mid. So I can show it to you on the screen too. It's that small baby. So basically, you can buy it on the TLHB or Suround distributor. But if you are an audio brand and you want to change something because you have a project which require a product close to it, but you would need a 4-ohm version, you would need a different FS, you would need aluminum cone, you would need something different. You can contact us directly and we will prototype it for you and we will produce it for you. We will put your brand on the product and we stay behind the scene, and next it will be your product and that's it. So this is the way we work.
Okay.
Next, there is a third
Can I just ask quickly, Clement, you mentioned the injected aluminium frame. Is this a metal injection molding?
Yes, absolutely.
So
absolutely,
a pretty expensive process or expensive tooling?
Yes, it's an expensive process. We do not do it internally. We selected 2 suppliers, exclusive suppliers for us. I mean, we do not work with the first supplier we meet. We take time to select and validate it and work with the process and so on. And now we are able to tool the frame you want. And because we worked very closely with the supplier, we succeed to reach a very competitive price. I think it's competitive for 5 or 6 inch aluminum frame. We are around $5,000 or $6,000 for the tooling.
Okay, so it becomes cheaper than trying to machine aluminium.
Yes, absolutely.
Okay.
If your quantity are some roughly 1,000 drivers every 18 months, it's cheaper to make a tooling than make a CNC or adapt something. We meet some situation where the customer try to adapt the parts to existing frame. And this huge limitation, because if you try to find a frame available on shelf, you have to consider the surround landing, the height between the spider and the surround landing to define the profile of your cone. And so you start your project with limitation. So this is important to say to the customer, we can do whatever you want. There are 2 limits. First is your creativity, and the second one is your budget. And so the creativity, we cannot do nothing. We can give our engineering and support and our own suggestion, but for the budget, we are a part of responsibility of that. So we try to be competitive and find the best supplier to supply the parts at the best price.
Okay.
For the products lineup we see on the screen now, all these frames has been produced for Kartesian exclusively. I mean, we designed this frame and it's our own tooling, and we produce it because we need some very specific frame. So this is a good example to show what we can do with the frame tooling. The driver we see on the screen is the third part of our product. It's a very special lineup named VKI. And so this driver are the sum up of all the innovation we developed during the last decade. So if I take one example on my hand, this one, you can see how the motor structure is large and the voice coil diameter is 80 millimeter. So you cannot find a 7-inch frame available on shelf, which allow to work with a 80 millimeter voice coil, basically because the whole of the frame will be too small. So I do not want to speak with too much detail about this lineup. You can check it on our website. For now, we have 4 references with 185 millimeter and 3 references with 265 millimeter. These drivers always use a short voice coil in a long gap, and the gap is made by magnet directly. There is no top plate and so on. It's a radial magnet motor structure. And I just use this short video to announce that there are new references to come by the end of this year. And this time we will do it a smaller version of the driver. So we succeeded to make the motor structure smaller, which will become less expensive. Okay. So I think it's enough for the introduction of the company and what we do. We can move on the topic. Just before moving to the topic, which is the spider limitation, I need to make a quick feedback about why we go into that topic. And the VKI lineup is a very good example of that. So the first idea was to improve the dynamic capacity of the transducer. Most of the time, we are looking on the frequency response, the THD of the driver, and we like that the frequency response is flat and the THD is low. These measurements are very important, of course, but it's not so relevant way of checking the driver quality because it's a static measurement. When you check the frequency response, you are just sweeping the frequency one by one, and you check the sound pressure coming out of the driver for every single frequency. And the music is completely different. The music is all the frequency together. So it's not a slow sweep. Even you do the sweep in 1 second, it's still slow for if you look at the acceleration, it's still slow compared to the random signal as music. For the THD, the same. THD is basically you play one frequency and you check and you measure the second harmonic, third harmonic, and so on, which is just a static measurement, and it doesn't exist in the real world. Mm-hmm. So in Kartesian, we try to move from the frequency domain to the time domain. And we do it for 2 reasons. First, the music is dynamic. It's not a frequency response, it's dynamic. It's a signal amplitude which is changing every time. And the second reason is the human ear is mainly a transient sensor. We do not work as a microphone. We are a transient sensor, and we have a very huge dynamic range capacity. It's from 20 micropascal to 200 pascal. So there is no sensor. I mean, there is no microphone able to measure such a wide range of pressure. The human ear is very exceptional sensor. So we should play with the rule of that sensor, not the rule of the microphone. To improve the performances of the dynamic, we move back from a white page and we created a new way to assemble the motor structure. Radial magnet already exists, yes, for a long time. but it was only a very thin radial magnet, because the way to assemble the radial magnet until now was to charge the magnet first and put it in the motor structure one by one. If you do it with thin magnet, it's complicated, but it's fine. But if you use thin magnet, you have a magnetic short circuit on the top and the bottom of the magnet. And so you lost maybe 30 to 40% of the height of the magnet because there is a magnetic short circuit on the top and bottom. So we decided to use a thick magnet. And with a thick magnet, you cannot play with charged magnet anymore. Otherwise, you will lose your fingers because it's too much powerful. So we spent 3 years to design our own magnet charger, and we are able to charge the radial magnet directly. And that is something very different than what already exists, because with thicker magnet, we increased the magnetic field a lot. And also we are much more efficient. We do not have this magnetic short circuit on top and bottom. Next, we put some Cooper spacer between the magnets to manage the inductance, and also aluminum and Cooper ring. I won't go into details right now. It's not the topic, but keep in mind, we changed the way to make the radial magnet motor structure, and this makes a lot of progress. What is important for now today is about the spider and the moving part. So for the spider, I will go into details later. And for the voice call, the cone, and so on, you can check our website directly if you want more information. The result of that technology, we have to measure it to prove it out that is real, because we are not working with marketing fantasy technology. We do not want to make a snake oil component. We want to measure it and prove it out. So we compare it with 37 woofers from competitors. And we did 3 categories. One is the VKI. The second one is what we name high quality woofer, is top of the art woofer. And the last one is regular woofer or vintage or esoteric woofer, this kind of stuff where there is no science behind. And what we see is VKI is not the best every time. For the THD in the low mid, for example, we do not have the lowest distortion, but on some other result as dynamic compression, we are much more better. And that's make a difference for the listening experience, because as I said previously, first the music is dynamic, and next your ear is a transient sensor, very sensitive with dynamic. The second point, I will go into details with the spider, is the TNS stability. It means that's very important. It means your drivers will work in the same way at low level and high level. If your TNS change according to the input signal, it means if you are playing a low level signal, you will have some specification, some response in the low frequency. And if you play at higher level, you will completely change the shape of the frequency response. And the last point as example is the modulation distortion. And we are not better on the full band, but in low frequency, we do a lot of improvements thanks to the motor structure and also thanks to the suspension that I will detail after. So
can we just go back and explain about the compression 95 dB 1 meter? What is the y-axis compression per dB? What is that? I don't know what that means. It's sometimes positive, sometimes negative.
Yes, absolutely. It's in decibel. So it means if the driver expand or compress the input signal. So the test is basic. You compare the input and the output. You increase step by step the input signal. In the very small signal, as let's say 0.2, 0.5 volt, you consider this is linear and it will be considered as a reference. And next, the signal increase. And so you can see if the increased signal is the same as the increase of the output. And if not, you have compression or expanded sound signal. And so this is the relation between the input and the output.
So it means that take this the black line, the regular woofer at low 50 hertz, let's say, whatever it's 45 hertz. As you increase the input level, you're actually getting greater output relative, like per input level, than at a low input level. And it goes.
Yes, absolutely. Because there is less control around the resonance frequency. And what you have is not related with the input signal. It's just because you have a mechanic resonator with typically with the AV cone, AV voice coil, and no control from the motor structure.
Interesting. Okay, thanks.
So with that kind of woofer, it means you lost completely the control of the bass. What you have could be impressive, yes, because you will have a lot of pressure in low frequency, but it will make a boomy sounding and you have no control. You cannot play any nuances in the bass with that. And what we see is next in the low mid, most of the time you have a compression because the cone movement is not able to follow what is requested by the voice coil. And this is just one graph, but it should be interesting to show other graph because this is 95 decibel, but it becomes more interesting at 100, 105, 110, where the real problems appear. We took 95 because next, some competitors, especially with regular technology, cannot play louder. After that, we have 5, 6, 7 decibel compression, so it's not fair. We want to compare where the products are in their recommended way of working. If I took a competitor suitable for plus or minus 5 millimeter excursion, I have to keep this limitation to make the comparison. Otherwise, it's not fair. So it's what we did.
Awesome. Thanks.
Yeah.
There is the full study available on our website. We have a PDF with that, and you have a lot of graph, all the details about the comparison and so on.
Okay.
So now we can start the topic, of today about the spider limitation, the consequences. We will move through 4 topics: the context and the limitation of the regular design, and also we will take a look on the surround stiffness because spider is not alone. And to finish, we will took some example with the spider technology we designed to solve that issue. So the context. I believe people watching this video already know that the main function of the spider is to keep the voice coil center in the gap and set the resonance frequency of the driver. It's not completely true to set the resonance frequency because it also depends on the surround stiffness and the moving mass, obviously. But in most of the driver, if you don't use a very stiff surround, as many low-cost driver where you have a very stiff surround which dam the cone and so on, and kill the dynamic range, by the way, the resonance frequency is mainly set by the spider. The spider is 3 to 5 times stiffer than the surround, usually. So the function of the spider are very basic. It's just mechanical parts to center the voice coil, and its stiffness will define the resonance frequency. So at that step, we could say, okay, it's a basic part. There is nothing to go into deeper engineering with that. It's something basic. So just take one spider on shelf and use it for your driver, and it will be fine. And this is what most of the driver manufacturer do for a century, but maybe we should do a little bit more engineering with that to make greater drivers. To explain the limitation, I will take an example of a very good driver and check the main nonlinearity and distortion of that driver. So this woofer is a very good woofer. There is nothing to blame with that. It's an excellent woofer, which is even better with the THD in a low mid than many Cartesian drivers. We can see the BL factor. It's very wide, over more or less 8 millimeter. The spider is very symmetric, which is nearly perfect. It is perfect. In fact, we cannot do something better than that. But we can see the THD, it's very, very low. It's maybe the best of the market currently in the low mid. But as every driver in the world, we can see the THD increasing a lot in low frequency. And so the question is, why should be proud of low THD in the low mid if the main THD is located in the low frequency, and this topic has not been addressed yet? So for me, it doesn't make sense to save 0.5% THD in the low mid if you still have 10% in the bass. So keep in mind that the stiffness variation of the spider is mainly responsible of the THD in low frequency. And to see that, we can move in the next graph provided by Klippel measurement. And so we can see, we can see the component of the THD. So on the X axis, we have time, which is, in fact, this test play pink noise signal with a boost at the resonance frequency, and the signal amplitude becomes larger and larger with time. And on the Y axis, we have the distortion components. So we see that with plus or minus 2% excursion, the spider is already responsible of the THD. And it will become worse at larger excursion around more or less 8 millimeter. We have 20 to 25% THD due to the spider exclusively. The force factor is in red. It's negligible. It's not negligible, but it's maybe 3%. The inductance is completely negligible. So the main problem is the spider. And this is most of the case for the high quality woofer, which has a good force factor, perfectly symmetric stiffness. Next, the next problem we meet is this stiffness increasing will also create the main part of the THD. So if, in fact, this is the case because we use also the stiffness of the spider as a protection for the driver. I will explain it just after. Before that, I want to show that the consequence of that. So if you change the stiffness of the spider according to the excursion, you will also change the TNS, because the resonance frequency is defined by the mass and the stiffness. The mass is constant, so if you increase the stiffness, you will increase the resonance frequency. Next, your QTS is dependent of the resonance frequency, so you will change the QTS as well. And so the modification of the stiffness will change your TNS, and it's not negligible. Do you have a question? No? Okay, so I continue. In that example, we see the difference between a typical hi-fi system in blue and typical pro audio driver in black. And next, we can see the modification of the frequency response in low frequency with this modification of the TNS. For this simulation, we only consider the modification of the key MS. We do not consider the BL decrease and so on. We only consider the key MS modification. We consider all the rest of the driver is perfect, which is not true, obviously, but it's already give us a good idea about what's happening. With only 14 decibel of dynamic range, if you take a woofer playing from 80 decibel to 100, you already have up to 2 decibel compression lost only because the stiffness of the spider changed the TNS, and this new TNS will provide a different shape of the low frequency response. So,
is it also fair? Can you frame that differently, just to say that as the stiffness varies, you're just going to change the waveform from the input waveform? Could it be said in that way?
Yes, we can. Yes, this is true. This is compression. What I'm showing here is the consequence of the small parameters variation on the low frequency response. If you design your enclosure with a vent and you consider your QTS is 0.4 and your resonance frequency is 40 Hertz, you will design the volume of your enclosure and the vent to reach a flat frequency response in the low frequency. And this is not true if your TNS parameter change according to the sound level. If the resonance frequency is 40 Hertz, when the excursion is more or less half millimeter, and it becomes 65 or 70, when the woofer is playing at more or less 6 millimeter, at the end, the low frequency response is not the same. It's completely changed. The tuning of the vent is not the same anymore. And so it completely changed the sound in low frequency. And this is very important because music is low and high signal playing together. So the good drivers, good products should play in the same way, the same frequency response at low level and high level.
Yep. Good.
So now there is a small delay. Sorry. Before going to that limitation, I want to add that in the Pro Audio, the stiffness variation is used as a limiter to avoid the driver damage, to avoid that the voice coil movement exceed what is suitable for proper working of the woofer. We increase the stiffness of the spider. In fact, it's a mechanical limiter. So it's something which is designed to protect the woofer. The point is we have to balance protection and linearity to avoid the dynamic compression and avoid the variation of the small parameter. About the dynamic compression, I take the same woofer as I took before. And this is what's happened if we play a signal with larger and larger signal. We see basically 3 steps. In the beginning, it's very linear. And at one point, we come into the compression part of the excursion. In that example, it's around 8 to 10 millimeter. Next, we cannot extend again the cone movement because the stiffness is so high that the motor structure doesn't have enough strength to compensate this stiffness. So even you have a very constant force factor with a variation around 10%, and your spider is changing its stiffness by 100%, it means it will slow down the movement of the cone under high excursion. So it's good because it's a protection, but it also set up a limit in dynamic capacity of the woofer. This is a good woofer. One more time, a very good woofer. So now if we take a look on a much more regular woofer, what we see is, first, we do not have a constant force factor. It's not symmetric. This excursion is not more or less 10 millimeter anymore. It's only 4 millimeter. And so what we see is the linear excursion is much more smaller. It's roughly 4 to 5 millimeter. Next, the driver is only compressed sound signal. And also we see an offset appearing in the graph on the left. This offset is due to the asymmetry of the spider mainly. So in that typical example, we see the spider become stiffer when the cone moves back. So it means the woofer will never move back. It will only move forward, and this will create the offset. The rest position of the drivers won't be the rest position without signal won't be the same as with signal, and this offset will create distortion as well. On the next graph, I'm going to explain a little bit about the compression and what I said previously with the pro audio protection. The graph on the left is the voltage compared with the displacement. So dash curve is a pure linear ratio between the input and the output. And what we see is when we increase the voltage, the output doesn't follow the input signal. So there is compression. The voltage in this example is huge. We are speaking about up to 20 volt in the free air. So it's a lot of power for a driver. But we can see that with only 5 volt, we reach the limit of the linear part of the driver. If we are looking on the graph on the right, we see the dynamic compression according to the frequency. And we see that for 20 volts, the compression reach 7 decibel in the low frequency and in the mid frequency. So this is not negligible at all. We can consider, for me, I could consider this driver linear up to, let's say, 12 volt or 10 or 12 volt maximum, which is a lot already. But it's necessary for the pro audio driver to increase the stiffness of the spider to protect the driver. Imagine this driver would be linear, the stiffness would be flat. It means that the excursion would reach maybe more or less 25 millimeter, which is not possible without damage on the woofer. So one more time, it's a protection. I'm not saying that everybody do it wrong. I explain that there is a limitation with spider stiffness, and for some topic, it's necessary to apply this stiffness curve increasing according to the cone excursion. There is one more point to consider with the stiffness is the spider is not alone. And the surround can be part of the problem. Typically with a regular half roll surround, we meet a surround asymmetry. The stiffness becomes higher when the cone moves back, and it's nearly constant when it moves forward. So if you use a spider which has typically the same issue, at the end, you meet a completely asymmetric stiffness, which produce the same THD as we described before. So I show it because it's very important to design the surround to also consider the stiffness shape. The surround is responsible of the sound radiation. The link between the cone and the surround must be engineered in details to avoid a typical dip around 1 kilohertz. The cone and the surround must play in phase on the useful bandwidth. We have to also take a look on the damping of the surround. And at the end, or not at the end, but we have also to consider the stiffness of this surround. and we should not consider the stiffness of the surround is lower than the spider, so whatever we do, it's still okay. This is not true. And with the engineering tool we have nowadays, I personally believe that everybody should consider this point. So the example I took is a woofer, nearly €200 per unit. And I cannot understand how that's possible at that price. It's not more expensive to design something good at that price. Anyway, so the message with this page is to keep in mind it's important to consider the stiffness of the surround. So now we can move on the conclusion. First, we see the stiffness variation is a root cause of the THD, especially in low frequency. We see that the KMS and the force factor, the ratio between both create the dynamic compression. And so to keep an offset-free driver, we have to increase the force factor where we increase the stiffness. Both curves should fit together. Increase the stiffness is a way to protect the woofer, and this is necessary for some application, especially in pro audio. And the last point is the surround and the spider must be engineered together to reach the right stiffness, symmetric, and as flat as possible is if we want to keep a very low nonlinearity. So how to do it? First, the preliminary step is to design a surround with symmetric stiffness. This is the example of the VKI driver I showed just before. On the left is the surround of this big boy with this large half roll surround. And so the stiffness is perfectly symmetric. And it's the same for the next, for another version we use for a more mid woofer to enlarge the surface area. The wide of the surround is smaller, and the stiffness is still very symmetric and nearly flat.
So, Clement, does that mean that is it limited to the materials, like the type of rubber, or do you just have to go shopping and find high quality either rubber or fabric surrounds to make that stiffness uniform or symmetric, as you say?
I think the geometry is more important than the material.
Okay.
The material will optimize the damping of the surround. It will help you to match the stiffness damping of the cone and the damping of the surround together to make the surround and the cone working together in the full boundaries without anti-phase mechanical behavior. But next, it's really the geometry which provide the stiffness. You can use whatever the hardness shore of the surround. If your geometry is correct, you will have a symmetric pattern of the stiffness. So
okay.
it depends on the radius of the surround. This is not just a half roll. It's not just one radius from the inside to the outside. There are 3 radius, and every single radius will change the stiffness according to the position. So we just have to play to reach a symmetric stiffness in the negative and positive excursion way.
Okay.
And with some materials, it becomes more complicated to reach this property. For example, with fabric or treated fabric, the damping material we apply on the fabrics make it complex to not to simulate, but to make it working properly in the real world.
Okay.
So next, if you have a surround which is a symmetric stiffness, you can work with different kind of spider. We designed 3 kind of spider. The first one is named dynamic. It's because it's the best to keep the full dynamic range and the full dynamic details of the driver because its stiffness is perfectly constant. The second one is named Pumax. It's allowed to keep the stiffness very linear, but next it protects the woofer, so it increased the maximum power. This why we name it Pumax. It's for maximum power. And the last one is progressive. Is the close to the one we see in the example of the top of the art woofer. It's a regular shape. We only engineer it to be sure this stiffness will be symmetric. And so it's a compromise between both dynamic and Pumax. So if we take concrete example, we can see on the left the dynamic spider, and the stiffness is perfectly flat around more or less 15 millimeter. So it's good for the performances of the driver. There is no TNS variation. There is no dynamic compression, but there is no protection either. So it means there is nothing to slow down the moving part if you use too high input signal. You can break the driver, basically. There is nothing to stop the cone movement. The limit is the signal input. So you have to really control the signal you use with that kind of driver. There is no issue if it's an active speaker typically, and if you use a DSP where you can control the excursion, this spider will provide the best performances. Or if you are able to control by yourself the volume on your amplifier, it's fine. But one more time, there is no protection. On the right, there is a Pumax spider. So on more or less maybe 10 millimeter, the stiffness is nearly flat, but next the stiffness will increase a lot, and we move into the protection part of the spider. I continue the example to explain that. So with the Pumax, we see in green, it's a pure linear part. In orange, it becomes to increase the stiffness. So there is a small excursion part where it's like a transition. And next is only protection. So the protection will create the dynamic compression. So this spider is a very interesting option for some high-end or monitoring studio or high-end hi-fi product. The transition between the linear part and the protection part must be worked or fine-tuned, because it means the driver is working with a very low nonlinearity. If you increase the excursion by 3 millimeter, you go into protection mode, which create compression. So the transition between linear and protection could be smooth according to your needs. To do it, we play with 2 spiders working together. So here are 2 examples. The first example is on the left is the dynamic and progressive together. So with that, we can see the final curve on the top is the stiffness is changing very smoothly on the full excursion. And on this example, the excursion is more or less 15 millimeters. So it's not negligible. The stiffness is only changing by 35% or on more or less 10 millimeter. So that means your driver will be protected, not high protection, but there is still a protection. And the linearity of the TNS and the compression will be very low. So it's a good compromise, and it's better than most of the woofer using regular spider. On the right, we use two spiders also. We use the PureMax technology and the progressive technology. In fact, the progressive will allow to make a smoother transition from the linear part of the stiffness to the protection part of the stiffness. But in this second example, the protection is higher than in the first one. So there is no perfect spider. What is important is to be able to find a solution which is perfectly suitable to the transducer purpose. If you are producing a pro audio driver or high-end driver, it's not the same purpose. And thanks to this spider technology, we can fine-tune the stiffness to match exactly what you want, and this makes a huge difference in the listening experience at the end, because the THD in low frequency, the TNS variation, so the shape of the frequency response in low frequency, and the dynamic compression will be adjusted and improved significantly. Next, I show concrete result, because this is graph and it's a simulation graph. So I take the example of the subwoofer. It's not the one I show to the screen. This is a subwoofer. So clip-L measurement of this subwoofer show force factor stiffness over more or less 15 millimeter. So we start with the stiffness, and we see the stiffness changing by 50% over more or less 15 millimeter. We see the beginning of the curve from more or less 5 millimeter is nearly flat. And next, we increase, not with a huge stiffness increase, we increase smoothly the stiffness to protect the driver, and only by 50%, not 100 or more, as we can see on other drivers with large excursion capacity. Mm-hmm. The force factor is not perfectly symmetric, and this is something we want to do because we want to match the stiffness and the force factor together to avoid any offset. And the last graph is the THD, not the THD, sorry. It's a second and third harmonic for 95 decibel 1 meter. And what we see is on the useful bandwidth up to 200 Hertz, the THD is lower than 1.5%. We have a second harmonic and third harmonic around 1%, which is very low. And it's a significant improvement compared to usual suspension technology. For this subwoofer, we have customers who use that sub up to 800 Hertz with a large mid-range. So yes, with this THD and performances, you could use this sub up to 800 Hertz. If we take a look on the dynamic behavior of that woofer, we can see the linear part of the woofer is up to more or less 15 millimeter. And next we start the compression part of the excursion. And there is no offset at all. Even at a more or less 20 millimeter excursion, there is no offset. On the graph on the left, we see that up to 105 decibel output, the dynamic compression is lower than 1 decibel. So this helps us to understand how important is the stiffness of the spider and the stiffness of the suspension. And we should not consider as I introduced the spider, it's not a basic component only there to center the voice coil and set the resonance frequency. It has a lot of consequences on the driver performances. So I hope I will pick up your curiosity, and I will motivate invited you to take a look more closely about the spider stiffness and this kind of non-linearity, because it has a lot of consequences on the performances of the driver.
Yeah, very interesting. I always understand the second time when I go through and edit these videos, but I would estimate that just based on what you said about the product categories you go after, studio monitor and small music venue playback, you're really trying to replicate the music and handle the output pressures of what like live sound needs to handle without distortion. So it's interesting approach to it, where rather than just not looking at frequency response curves and sine wave signals. So that's an interesting approach to it.
Yeah, absolutely. Nowadays with DSP, we have everyone can buy a DSP for some $100 and the microphone with the same price range, and you can play with that and reach a very flat frequency response. And if you believe that you built a perfect driver because you get a flat frequency response with the DSP, I believe this is absolutely wrong. We also have to consider what's happened in the time domain. And that can be improved by DSP, especially if you have a motion feedback sensor or something like that. But less the DSP is helping the driver and better the result is. So starting with a low nonlinearity driver for us is a fundamental starting point. And also most of the loudspeakers today are still passive speaker. So if you don't have anything to correct the drivers during the sound reproduction, so it's very important to work on that topic. For the motor structure, I can understand that it becomes expensive to make a very linear motor structure. Kartesian like a lot the short coil in the long gap. So if you use regular design with the magnet in the top plate, it means to get a stiff top plate and short coil, you need a big magnet to reach a correct B in the gap. Otherwise, you have to use a 3-4 layers voice coil, and you move back to many inductance issue. So okay, it's very expensive to build a good motor structure, but build a good suspension is not more expensive than design a completely a random spider or surround. At one point, you have the same material cost and you have the same tooling cost. Right. So the difference is the engineering time you spent. Maybe we are a little bit excessive. We spend a year to design the spider shape and try many material, check how the material of the spider will change according to the time, ensuring a long longevity with the same performances. Okay, maybe we are a little bit extreme, but this is our DNA to make every single component as perfect as we can. This is our soul, basically.
Yeah, and I would say beyond the technical, the commercial point that you made, that you pointed out the fact that you're not quite as good in THD, but you're better in this point. I always like somebody presenting their technology where they give people the nice balance of where you excel at. So I appreciate that.
Yes, it's true. The last years we have seen some new technology coming on the market. I do not want to name anyone because everybody knows who they are, and they I would like to make a hat, but I'm not allowed to do it. So many people did not many, but some drivers company did some improvement in the driver design, and some of them reach very good result. And for Kartesian, we do not consider these competitors as business competitors. We consider it as a challenger to motivate us to do something better. And we hope we will motivate them to make some progress again. And by challenging each other, together we will make the audio world progress. That's the way of thinking. So I would not claim we do the best driver of the world. That would be completely stupid. So every driver has his own purpose, and so it's just dedicated for one application. Next, what the message is, okay, the suspension is the point where the audio engineer should consider a little bit more of engineering, because there are a lot of issues due to this absolutely stupid part. It's just a part of fabric which is shaped by temperature, so it's nothing complicated, but it requires engineering.
Okay. All right, Simon, do you got any questions?
No questions. I'm just hoping to have a listen to a subwoofer with 1% THD at 30 hertz at high level. I think that must be impressive. I've heard a lot of sloppy subwoofers before. It's fun too, but something with low distortions, but going to have a special sound to it.
Yeah. One anecdote about it. When we design a driver, we built a concept-proof product. So for this subwoofer, this 7-inch subwoofer, we did a small sealed enclosure with a huge Class D amplifier with DSP integrated. And we generated with the DSP some artificial THD to see what's happened. And the conclusion was the THD is not the point which make which disturb the most the listening experience. If you had some THD in low frequency, you will change the color of the sound, I will say. With more THD, especially with second harmonic, the bass become more impressive sometimes. Okay, it's less natural. I'm speaking as an audiophile. I'm sorry, I'm an engineer, but everyone will understand what I mean. There are some algorithms who work with the harmonic in low frequency to, there is a missing fundamental theorem about it. It will make believe your brain that bass are generated, but there is not. It's just the harmonics who will help your brain to create the fundamental, which is not playing anymore. So if you had some THD in low frequency, and if you are lucky, you can get this kind of result and make your brain believing that there is more bass and the bass become more impressive. What really convince us that it's important to continue our engineering with suspension and motor structure is the dynamic compression. It's if you had a limiter, it's much more audible than add some THD. If you play some, including electronic music, and you have a very huge dynamic range, and next you add artificial limiter with the DSP, and you listen again, and the listening experience become boring because it's not living anymore. It's not the same at all. So really the dynamic compression for me it's something very, very important. That's what we most consider in the listening experience. And when we do it with blind test.
Cool.
So
interesting.
All right. So Clement, I guess let's call it a day here. We've spent an hours of people time teaching everybody about Kartesian speakers. So yeah, thank you so much for joining us today. We appreciate that. We'll put some links for everybody down below where they can follow up and get some more details if they're interested, and like, subscribe, all that good stuff. We'll see everybody on the next episode. Thanks. Bye-bye.